But this is admittedly a very tough problem because there's a lot of things to think about, right? First of all, we can assume that K1 of the other species isn't changing because we said that before. It's relatively constant with temperature. And so if that's the case, the only thing that matters is what's going on with these two variables here. But the interesting key here is it's the product of the two that matters. And so what happens is, if you're down here at low temperatures and you have a very small alpha, you take a very small number that's a fraction, less than 1, which is what alpha is. In fact, if we go back a slide, we can see that it's less than 0.1 alpha. So if we think about it like that, we're taking a very small fraction and multiplying it by a whole number. And what we get is a very small number. And so this is likely to be small at low temperatures, which is good for paramecium because we want this to be less than K1. Now, if we think about the other side of things, what we have is a very large number of alpha and a very small whole number of K. But the number of alpha when it's large, again, go back a slide, large is 0.5, so it's still a fraction. And so what we can imagine is that you've got a large fraction multiplied by a very small whole number, yielding a very small whole number, right? And now that means that at high temperatures, this product, at high temperatures, this product is also small. But now let's shift towards the middle. Now we have a moderate-sized fraction multiplied by a moderate-sized whole number. And what we end up getting is the largest product somewhere in the middle of the temperatures, right? Somewhere in the middle of the range. And so if we go to that question, paramecium are most likely to persist at intermediate temperatures, it's actually false. That's where the competitive effect of coppidium is probably going to be the largest because there's a decent number of coppidium and there's a moderate competitive effect. And the product of those two is going to yield a larger number than it would at the extreme temperatures where either the competitive effect or the number of coppidium is going to be small. And so the products will be small. OK, hopefully that makes sense. If not, rewind about 5 minutes and watch it again and see if you can follow it a second time. This is, in fact, a difficult concept. And so I'll draw it out for you. Graphically, what we're saying here is, in this area here, yes, paramecium will persist because the product between these two things, this alpha and this K2, is going to likely be less than K1. Here also, yes, they're going to persist because of the same thing. In the middle, no, because when you have large numbers of both, or moderate numbers of both, the product is going to be greater, and perhaps greater than K. And so our guess should be this is the most likely region where paramecium will go extinct if we compete it with coppidium. Now, great. This is an application of a model, and you can see where the theory lends to predictions, but it's only worth something if the model actually makes a prediction that we can verify experimentally. So that, of course, is the next step. And here are data for actual populations of coppidium and paramecium grown together in a flask, replicated, of course. And what I want to show you are these data at 22, 26, and 30 degrees Celsius. That is the low end of the range, the middle, and the high end of the range. Remember, the legend here shows you that the black dots are for coppidium, the open dots are for paramecium. We predicted paramecium was most likely to persist at the extremes and least likely to persist in the middle. Now take a minute or two and write a figure legend and tell me, if that prediction was upheld.